Chapter 9 covers linear momentum. We're going to get into angular momentum later on, but the primary focus on this is linear momentum, collisions, the interactions between two objects putting a force on one another, and also this concept of a conservation number, conservation of momentum. So uh, again, linear momentum, we need to define what it is, first of all, and why it's important to talk about. So linear momentum is simply the product of a scalar, and that's mass, times the velocity. So this is sort of a measure of motion. The more mass something has, the more inertia it has, the more difficult it is to change its motion. The more we increase the velocity, the more we increase the speed of an object, the more difficult it is to bring to rest. So in linear momentum, the units are very simple. They're either kilograms, meters per second, and that just is reflected in the product of mass and velocity. But when we look at impulse, we'll also see that we're taking a force and time, and it's not hard to convert kilograms, meters per second to Newton's times seconds. Newtons, of course, are kilograms, meters per second squared. If I multiply by seconds, the denominator changes from seconds squared to seconds, and I get Newton seconds. CGS units are grams, centimeters per second, and the US customary units are pound seconds. So that's sort of an awkward unit, but that is the US customary unit. Momentum is always conserved. That's going to be a very big idea throughout this chapter. In fact, we will be using conservation of momentum to find unknowns in particular problems. This is a consequence of Newton's third law, as we'll see. Any action is complemented by an equal and opposite reaction. So if I put one force on another object, that force will be placed on the first object, and the transfer momentum will be equal and opposite, just as the forces are equal and opposite, and this conserves momentum. Momentum being a product of mass and velocity. Mass is a scalar, it has no direction. So simply the direction of the velocity is also the direction of the momentum. For instance, if I have a mass traveling with 10 kilograms of mass, and it's traveling 5 meters per second in the x direction, our momentum is also going to be in the x direction. I just take the product of the magnitude of our velocity and the mass, and I get 50 meters per second, again, in the x direction. So if you know the direction of the velocity, you know the direction of the momentum, and vice versa. Traditionally, we can write momentum in terms of its orthogonal components. If we're adding different momenta together, we need to add the orthogonal components together individually. The x's go with the x's, the y's go with y's, the z's go with the z's, and it adds together just like any other vector that we have. Frame of reference. This is important. Our momentum, because our velocity depends on a frame of reference, our momentum is also going to depend on our frame of reference. So if I have some object and it's stationary in, let's say, one frame of reference, one inertial frame of reference, let's say this black frame of reference right here, if it's not moving, then obviously the object has no momentum in that frame of reference. However, in a moving frame of reference, and this can still be an inertial frame of reference, meaning it's not accelerating, if this frame of reference is moving with respect to the first frame of reference, then obviously this green object has to move in the opposite direction, and therefore it has momentum. So linear momentum is conserved in an inertial frame of reference, meaning that whatever the momentum is in the black frame of reference or the prime frame of reference, it will be conserved, as long as it's a closed system. However, we can't say that linear momentum would be conserved in a frame of reference that's not inertial. Let's say we're talking about an accelerating frame of reference, then we don't get conservation of momentum. Just doing some quick calculations. Here, we're looking at 105 mile per hour fastball, which was supposedly the fastest fastball ever thrown in a baseball game. The mass of a baseball is 145 grams. We multiply that times the magnitude of the velocity, the speed. We get a magnitude for the momentum of 6.82 kilograms meters per second. Fairly easy object to stop because it doesn't have all that much momentum. However, as we look at more massive objects traveling at different velocities, we see that the momentum can become more significant. For instance, a person sprinting at a world-class speed, 10 meters per second would be world-class speed there. Let's say that they're 60 kilograms sprinting at 10 meters per second. There, the momentum again is just the product of the two. So our magnitude for the momentum would be 600 kilograms meters per second. Car, now typical car at 1,500 kilograms. Obviously, the momentum is going to depend on its speed, on its velocity in the frame of reference that we're looking at. So 25 miles per hour, this car would have about 16,000 to 17,000 kilograms meters per second of momentum. At 55 miles per hour, that's 25 meters per second roughly, a little more than twice the speed. We're going to get twice the momentum. At 75 miles per hour, the momentum is around 50,000 kilograms meters per second. Now, again, it's important to understand that momentum is sort of a measure of motion. So when we talk about the momentum that something has, the amount of momentum that it has really tells you how difficult it is to bring that object to rest. We'll use forces to do that, and we'll see that there's a different way of writing Newton's second law, but we'll just, again, keep this very simple at this point. We're well aware that cars can stop much easier than, let's say, a more massive object like an 18-wheeler, which has a mass typically of about 25,000 kilograms. So here, for the same speeds that we used in the previous example, we can see that the magnitude of the momentum is proportionally larger related to the mass. Even at 25 meters per second, 25 miles per hour, it would have a momentum much greater than a car traveling at 75 miles per hour. So bringing this truck to rest is much more difficult. And that's why drivers have to be aware when you're talking about a more massive vehicle on the road, we have to be aware that, stopping quickly in front of a truck is really creating a very difficult situation for the truck driver and yourself because of the large amount of momentum that's involved. You double the speed, the momentum is going to double, and certainly a truck traveling at 75 miles per hour, that's 33.5 meters per second, has almost 1,000,000 kilogram meters per second in momentum and would take a tremendous amount of force and time to bring to rest. So that's basically our introduction to momentum. One last example here. This is the USS New Jersey, which is now a museum. It used to fire some of the largest shells ever fired by a warship. 1,200 kilograms was the mass of the shells, and they'd be launched at a speed of 820 meters per second. Obviously, such a large mass at such a large velocity would produce a very large momentum. In this case, 9.8 times 10 to the fifth kilograms meters per second. Again, almost 1,000,000 kilograms meters per second for the shell being launched at that velocity. Okay? So again, that's our introduction to momentum. Here, again, we can see that the magnitude of momentum is really easy to calculate. And of course, if you know the direction of our velocity, our direction of momentum is in the same direction.